Very good. So we talked about the muon collider, or in general, the reason why we're going to go to 10 TeV center mass energy is a way of fully understand electroweak symmetry breaking. So basically, the idea is that here's the potential, X potential, and the vacuum is here. And that's where we live. And thanks to the Large Hadron Collider now, we managed to produce excitation of the Higgs boson, which is the fluctuation around the vacuum up to the quadratic order. So that's the Higgs boson. But we are basically stuck in this area. And then what we discussed yesterday is really take this vantage point of going way up here and then look down. This is meant to be an eye. I'm not doing this very well. So look down on this the ground state, so that at this vantage point, SU2 cross U1 is basically recovered. And looking down at the ground state or vacuum of the standard model, you can tell that, okay, nature actually is SU2 cross U1 symmetric. We don't see that in a vacuum, but it actually is, because we now see W plus W minus Z together with Higgs all behaving the same way as a 4-component multiplet of an enhanced symmetry. And then we can really understand how exactly they actually interact with each other. And to be able to actually do these tests, we talked about the fact that the scattering process in this W and Higgs sector is crucial, which in particular involves Higgs self-coupling as well. And the idea is to attach this to some fermions as external states, which could be muon or electron or some quark, depending on what collider we are going to build at the end of the day. And so that's why we wanted to actually talk about going well above the electroweak scale to understand it actually a lot better. So that's what we talked about yesterday. But in addition to that, the argument, there's also a possibility of thinking about new physics. And so in order to understand electroweak symmetry breaking, we really talked about the fact that we want to go to some deeper theory. I mentioned Technicolor as a failed attempt to do so, but nonetheless, we are going to some energy scale much bigger than the MZ, so that we have a fundamental understanding on where electroweak symmetry breaking is actually coming from. But in addition, there has been very strong argument based on the idea called naturalness, and also the fact that we are still uncomfortable talking about elementary spin zero particle. So I'd like to go through these arguments and why that would actually imply new physics at some energy scale. And of course, you may argue that the naturalness idea, we heard it before, but somehow that was used as an argument to justify supersymmetry at the Large Hadron Collider, but that didn't pan out. So maybe the whole argument is now discredited. And of course, you can take that point of view too. But what I'd like to tell you now is that at least you need to know what naturalness argument has been and how that is related to the ideas we talked about so far, like technical and supersymmetry, and whether that would actually turn out to be a good guidance for future development of the field is, of course, left up to you. But at least you need to hear the argument. And I myself still take it seriously. But I also realize that have been probably overused and overemphasized when we may have been actually thinking about it not in the correct way, and we can briefly touch on that too. But at least I wanted to just briefly talk about what naturalist argument actually is, and if that is actually something useful when we talk about 10 TeV partner center mass energy scale physics, and that would potentially lead to discovery of whole new set of particles or symmetries. So that would be, of course, very, very exciting. So that is what I'd like to discuss first. So what is naturalness? So I always discuss an example in classical electromagnetism when I talk about naturalness. Because when you have an electron which of course was discovered by J.J. Thomson back at the end of the 19th century. And Max already told us the theory of electromagnetism. We know right away, once the electron is discovered, that the electron creates a Coulomb field around it. And so what that means is that the electron actually can feel its own Coulomb field and acquires a correction to its energy, which is roughly e squared over 4 pi times the size of the electron. And you can make this calculation a bit more precisely by assuming that the electron has a finite radius RE with a constant charge density. Then you can compute how much it would take to bring a next shell of the charge to the charge that already exists at the center and keep doing it shell by shell and compute the total energy that is required to do so. Basically, that the like charges repel. So in order to contain the repelling like charges into small volume, you do have to put a lot of energy into the system. So that is the rough estimate of the correction to the energy of the electron. And if I write this in terms of the natural unit, then this is alpha. E squared of 4 pi is alpha, or epsilon naught if you like the SI unit, and h bar c over the size of the electron, and that gives you the right unit. And if you don't know what h bar c is, you're not serious particle physicists. You should remember this. H bar c is 0.197 GeV times femtometer, and femtometer is often called also a Fermi. So that's the unit for distance scale. GeV, of course, the unit for the energy scale. And 0.197 is kind of easy to remember because you know the fine structure constant is 1 over 137. You just change 3 to 9, that's 197. So that's the way I end up remembering this number. And the reason I'm talking about this is that now comes the comparison between this correction versus the total energy of the electron at rest, that is mc squared. So if you imagine the size of the electron is very small, then in order to keep it in one piece to contain all of its electric charge, you need to provide this much energy to the system. And once you make the electron smaller and smaller, at some point, the Coulomb energy would saturate the energy of the electron. So that energy can, the distance scale can be easily estimated because R sub E, size of the electron, once that is actually smaller than alpha h bar c over mac squared, then that would saturate or maybe oversaturate the total energy of the electron, namely its rest energy. And knowing this is 0.1511 MeV, this is 1 over 137. We just talked about 197 GeV Fermi. And an order of magnitude estimate is that this is basically a Fermi, 10 to the minus 13 centimeter. So once the electron becomes as small as the size of the proton or neutron, then the Coulomb energy would end up saturating the total mass of the electron. And as a matter of fact, we already know from experiment that size of the electron has to be smaller than 10 to the minus 17 centimeters. And if you plug this number into the expression for the Coulomb self-energy, again, you can use the same formula, 0.197 GeV Fermi, 10 to the minus 17 centimeters. So that is actually 10 to the minus 10 to the minus 4 Fermi. So that would end up actually giving you something of the order of a GeV. And if you actually buy into this estimate, then you have to assume that the rest energy of the electron we observe is some kind of the sum of the rest energy of the electron of a bare electron, where you strip off all the effect of the Coulomb field around it, and the correction due to the Coulomb field. And I told you that this is about GeV to the extent we know the size of the electron, and we know this is 0.511 MeV. So then what you have to assume, though, is that the bare mass of the electron is negative GeV. You cancel four significant digits between them so that you can end up with 0.5 MeV instead. So that sounds ridiculous. As a matter of fact, when you actually open up the textbook by Landau and Lifshitz, classical theory of fields, you find a statement about this, what they call the self-energy problem. Of electron, and they claim that theory of electromagnetism breaks down at distance scale below 10 to minus 13 centimeters. So this, they couldn't accept this miraculous cancellation between two numbers, and therefore the best you can think of is that the size of electron is to this extent that it ends up saturating the total energy of the electron, and that's as much you can go using the theory of electromagnetism, and hence this statement. And when I actually read this statement back in a grad school, I think it was my first year, I noticed that there was an asterisk here, and there was a footnote. And the footnote had something along the line of, but this problem does not exist in quantum theory. And no further elaboration on this. And I was totally baffled. What are they talking about here? And why does the quantum theory change this estimate? And why does the problem disappear at all? And it took me actually several years to understand what they meant by this. So here is what actually they meant, at least to the extent I could understand. So the idea is that once we have a quantum theory, there is an uncertainty principle. We all know that. In particular, there's an uncertainty principle that says delta E, delta T is order H bar, namely that you can actually borrow energy as long as you can return it within the time allowed by the uncertainty principle, that is H bar over delta T. So if you can borrow a lot of energy if you actually return it as quickly as you can. So that's what the quantum theory tells us. At the same time, second, when quantum got married with relativity, that is what Dirac did with Dirac theory, and that predicted antimatter. So in the case of electron, there is a positron. So what that means in then is that what we think is the empty space is constantly producing a pair of electron and positron together with a photon. And by producing a pair of electron and positron, that of course costs you extra energy of the twice the rest energy of the electron. So you are borrowing energy, but the quantum theory tells us it's okay to do that as long as you give it back quickly. And what we think is empty space is actually doing this all the time. It spontaneously creates a virtual pair of electron positron, and they quickly annihilate back back to nothing. But this is actually what is going on in empty space all the time. So now comes the following question. So when you talk about energy of the electron, and you can see that electron can create a Coulomb field around it, and can feel its own Coulomb field. So this correction we talked about, namely alpha over R, is something that can be depicted by this diagram. But here you need to be aware that this happens first because the electron creates a Coulomb field, otherwise it can't feel it. So there's a definite time ordering here. On the other hand, we just talked about the fact that the vacuum is doing this, the constant creation of electron-positron all the time. And in that empty space, we think, you place an electron. And once in a while, the electron you put into the space realizes that there is actually positron around it. So this electron may decide to annihilate this positron that used to be part of this fluctuation of the empty space or vacuum fluctuation. As a result, the process that can happen is the following. So here, the vacuum spontaneously creates electron, positron, and photon. Here's the electron you placed inside this vacuum. And then this electron notices this positron within the quantum fluctuation and decides to annihilate it. And the other electron that used to be part of this vacuum fluctuation now remains as a real electron. And if you go ahead and calculate this process, it turns out that this is almost exactly the same size, except that has a negative sign to it. Now, that sounds too miraculous, but this is actually true. And at the end of the day, if you sum both of these contributions up, you find that correction to the electron energy turns out to be proportional to the mass itself times only logarithmic correction rather than this linearly divergent correction, which goes together with size of the electron, which may be cut off by the smallest distance we can imagine, like the Planck scale. And if you put in the Planck scale here, and the size of the electron we know, like 10 to minus 17 centimeter from the experiments already, together with alpha and MEC squared, this actually turns out to be something like 10% of MEC squared. So that's when we find that the bare mass of the electron plus correction is something like 0.19 plus 0.1 is 1 in the unit of the observed mass of the electron. So then it doesn't look like there's a problem anymore because you don't need to either fine-tune parameters to get the precise cancellation between two numbers, or you can actually even send the size of electron all the way to the size of the Planck scale, and you have only 10% correction. So this is the way the Landau-Lipschitz argued that this problem doesn't exist in quantum theory. And it took me actually several years for me to figure this out. So what that means is that is the criteria in the end have been formalized by TeV, the concept called technical naturalness. Namely that in the case of QED, and if you look at the Lagrangian, and psi is the electron field, you all know this Lagrangian, and here's the mass of the electron. And when you actually send the mass of the electron to 0, then this piece here actually decouples into two wire fermions, left and right. And you find a symmetry of rotating left-handed field and right-hand field by the opposite phase. Normally we put this sign here, which can also be written using gamma 5 matrix, because gamma 5 matrix has an eigenvalue of +1 on the right-handed component, -1 on the left-handed component. So this is actually the same thing. And this is nothing but what we call the chiral symmetry. Namely, in the limit where mass of the electron goes to 0, you have an enhanced symmetry of the system. And because the electron mass being the only parameter in the theory that actually explicitly break chiral symmetry, no matter what correction you ask, turned out to be proportional to the parameter that breaks the chiral symmetry times some dimensionless number, which we found to be something like alpha 2 pi times log. So this is the way we now understand why there was an exact cancellation between two contributions to the self-energy of the electron. And these days, when you open the QFT textbook, you can see that this time ordering and this time ordering is just the opposite from each other. So you actually are computing some of the two when you draw a Feynman diagram for the self-energy, because the Feynman diagram already sums two possible time orderings between these two vertices. So you don't think about this linear divergence anymore, because automatically the result comes out to be only logarithmic diversion. And that's something I'm sure you have done exercise in QFT class. So that's what's going on here. So once you have a situation where symmetry is enhanced when you turn off certain parameter, and that parameter is protected against an additive correction and receives only a multiplicative correction, namely that correction is always proportional to the parameter you are studying. And that's why we can talk about percentage correction instead of adding a big number to a very negative number to get a small number at the end of the day. So this is a situation TeV defined as a technical naturalness, namely the smallness of the electron mass is protected against radiative corrections, against loop diagrams, because setting electrons to zero corresponds to an enhanced symmetry. Now, this kind of situation can happen in many different ways. And now let me jump into the case of supersymmetry and talk about the Higgs boson. So we have this Higgs potential, and Higgs potential has this to the, so you have this interaction of the 4-point vertex among Higgs bosons. We talked about this yesterday. And this actually self-repelling interaction is crucial to understand the stability of the vacuum. Listen to a talk of Bose-Einstein condensate of dilute ultra-cold gas of atoms. You have these atoms moving in a gas, let's say at some high temperature, so they're moving very, very fast, totally independent from each other. But as you cool the temperature, they start to move more slowly. And when they're moving slowly, Dubray wavelength of individual atoms is the Planck constant divided by its momentum. I'm talking about non-relativistic particle here. And the velocity, of course, goes down as you cool the system, and therefore the Dubray wavelength actually goes up. So at some point, the wavelength of these individual atoms becomes so big, so they start to overlap with each other. And then they, in the end, form a single wave, which is the matter wave. And this is what Bose-Einstein condensate is, namely that the collection of atoms at a very cold temperature behave as if it were a single classical wave. And that's why when you actually draw and then overlap, you see a fringe pattern in them. So it's not that single particle behaves like a wave, that is what follows the Schrödinger equation. But in this case, thousands or tens of thousands of atoms together behave as a single wave, and that is what is called the condensate, Bose-Einstein condensate. So what we think is that Higgs boson followed the same fate. The Higgs boson was, moving about in a very fast motion in the early universe, But as the temperature cooled, it started to actually move very, very slowly with each other. And eventually the Broglie wavelength of the individual Higgs boson starts to overlap. And the entire universe gets covered by this classical field. And that's what the electrosymmetry breaking is supposed to be. But for this to be a stable condensate, then they have to repel with each other. Because the sign of this, the phi to the fourth coupling is nothing but the repulsive force among the Higgs boson particles. So in fact, in the laboratory where people study this dilute outer core gas of atoms, there's something called the Feshbach resonance that allows you to oops, and bounces back in a big explosion. And you can observe that. And this big explosion is what they call bosonova, sort of the similar idea of the supernova explosion, which is based on the dense generic gas of the neutrons in a Fermi degenerate way. So that is actually Fermi nova. But in this case, it's the BEC that actually explodes, and it's called the bosonova. So the fact that you have this positive quartic potential is really crucial for our universe to be stable. But this crucial self-interaction ends up causing this problem, because once you have this self-coupling here, you can easily compute this one-loop diagram, and that generates the correction to the mass of the Higgs boson, which is quadratically divergent. And this lambda is meant to be some kind of UV cutoff. And if you'd like to do the analogy to the previous example I talked about, you may regard this to be 1 over the size of the Higgs boson, so to speak. So then you have the same problem we had with the electron before. And in this case, the 't Hooft argument doesn't really work, because turning on the mass of the Higgs boson doesn't make the symmetry of this theory bigger. And some of you might complain, well, the Higgs mass is the only dimension 4 parameter in the standard model. Setting to 0 actually doesn't enhance the symmetry, because now theory is classically scale invariant or conformally invariant. And, well, that's actually true, except for the fact that we know the conformal invariance doesn't exist in the standard model, because the coupling constants run. We talked about this confinement scale yesterday, and alpha sub s actually blows up some energy scale. There is the energy scale, which is secretly there in the standard model. So, conformal invariance actually doesn't get recovered, even if you send the mass of the Higgs boson over 0. So in the end, it doesn't protect us from anything. So that is actually a situation very similar to the classical electromagnetism. And what supersymmetry does is, just like we introduced the antimatter to solve the problem of the electron mass, we double the number of particles once again. Then every particle, like Higgs, has a superpartner fermion, Higgs CNO, or W boson also has a superpartner of the we know, top quark has a superpartner of a stop. So in addition to this diagram I mentioned earlier, there are also other diagrams like W exchange and topic loop. They all give you these quadratic divergences, and then we have to somehow cope with them. But for each one of them, it turns out the Higgs can go to Higgsino and we know, or Higgs can have the loop of scalar top, in addition to the loop of the Higgs boson we talked about. And if you sum all of them together, again, the correction turns out to be log. And the way that works is that in the limit, supersymmetry is exact. The correction to Higgs mass vanishes. So this gets induced only to the extent the supersymmetry is actually broken. And if you actually sum of these diagrams up, and of course these diagrams depend on the mass of the Wiener, mass of the scalar top, and so on and so forth. And the fact that mass of the Wiener is different from the mass of the W tells you that the supersymmetry is actually broken in nature. And the correction turns out to be proportional to that. So as a result, correction to Higgs mass is something like alpha over 2 pi, supersymmetry breaking scale squared times the logarithm. So now you see very clearly, the minute you actually turn this 0, then this also goes to 0. And that is proof technical naturalness. Because in the limit where supersymmetry becomes exact, then there is actually no correction. Therefore, the only correction that gets induced is proportional to the violation of supersymmetry. And that was the cornerstone of the argument why people hoped that the supersymmetry is below TeV energy scale. Because when you put this alpha 2 pi and logarithm, assuming the cutoff scale is very high, like the Planck scale or Gutt scale, this combination is something like order 1. So this may be 10 to the minus 2, but this may be of the order of 100. So product is about order 1. So in order to keep the Higgs mass itself below the TeV energy scale, then we want this SUSY scale to be below TeV. And that was the argument of the naturalness requiring supersymmetry. And we all expected that to be visible and detectable at the Large Hadron Collider. And in retrospect, it is actually even amusing that when we were preparing for the Large Hadron Collider, then the Higgs mass of 125 GeV has always been an iffy issue. So people argued a lot whether the Higgs mass below 140 GeV can ever be detected at the Large Hadron Collider because the decay products like photon or for leptons become so soft. And in very complicated environment, have many jets around it, can we really pick it up and observe it? And so that was meant to be actually a very difficult signal that may take years on LSC. We get overwhelmed by the signal of all these new superparticles. And that would actually make the search for the Higgs boson even more difficult because there's a huge background coming from the decays of supersymmetric particles. So now in retrospect, it feels so funny that we've been talking about this. But anyway, so that was the expectation way before the OSC turned on. So that certainly was wrong. And we all admit that was wrong. This idea probably had been oversold. So we need to take it with some grain of salt. But I hope that I made it clear that this actually still has a relevance because whenever we think of some new physics happening at a very high energy scale, you really would like to protect it from having a quadratic correction, but rather have only logarithmic correction. So the same disease is something I mentioned also yesterday, that when you think of non-supersymmetric standard model at the face value, then at some very high cutoff scale, you need to have Higgs mass of the order of the cutoff scale. And because of this quadratic divergence I mentioned earlier, the running is straight line in energy squared. And if you think of this energy scale to be, say, Gutt scale, that's 10 to the 36, 10 to the 32 GeV squared, you start with a 10 to the 32 GeV squared, and you do a straight line and make sure that you find a number of the order of 10 to the 4 GeV squared. And that would require this initial value and the slope to be tuned at the level 10 to the minus 28. So that is the situation we indeed have when you don't have supersymmetry. While if you do have it, then it's correct, it's protected because the correction turns out to be only logarithmic. And that's why we could also draw another picture yesterday, that now we are talking about the logarithmic energy scale, and superparticle masses like quark and leptons are enhanced at low energies, but Higgs mass squared actually crosses zero and goes negative at low energies. And that actually explains why SU2 cross U1 is the symmetry that was broken in the end, while SU3 color or U1 QED are not broken. So that is what we meant as a one-step deeper theory to understand electric symmetry breaking. But not only that it provides this explanation, it also provides this extra protection on the energy scale of the Higgs boson. So that was the argument of the naturalness. And of course, there could be another possibility how this energy scale could be protected. And that's a case of compositeness. And if you think about the pi plus, it actually does have quadratic divergence in its mass squared because it has electric charge. But this correction to electric charge is given by, of course, something proportional to alpha. But in this case, there is literally the size of the pion, because it's a composite object, and size of the pion is something of the order of 0.6 Fermi. And again, if you put this number in, you can work it out. And then that correction turns out to be really of the correct size to explain the difference between pi plus minus masses and pi zero masses. So this effect is actually observed, but we know it's small. It's only 140 MeV squared minus 135 MeV squared, right? And that is clearly explained by this kind of order of magnitude estimate. So what's happening here is that, well, there is a quadratic divergence, but because the pion has a finite size, that quadratic divergence is cut off by its size, and that's determined by the QCD scale. And once you actually get in further into shorter and shorter distance scale, then pion is no longer an elementary particle anymore, it's composite. What you actually start to see is the quark, and the mass of the quark we have seen is protected by the same chiral symmetry like the mass of the electron that is protected in QED. So above this energy scale, then corrections only become logarithmic. So what is going on here is that you have this power correction initially, but then it gets tamed down only with logarithmic behavior. And then there is actually no problem to understand the mass of the charged pion anymore. So this is another way that there is a protection on the mass of certain objects, so that's because of the finite physical size. And so that actually also led to the speculation that Higgs boson may also be some kind of composite object. And if the constituents of the composite object is spin 1/2, then there is a chiral symmetry associated with the spin 1/2.
Hitoshi, we lost your sound.
Do that. Oops. Something happened?
Yeah, we lost your sound for a while. I think you were
Okay.
explaining the radius of the Higgs.
Okay, so Higgs mass squared is actually protected by the finite size of the Higgs itself as a composite object up to the composite scale. And above that energy scale, or the shorter distance scales, you are observing the constituents directly. And if the constituent is the one spin 1/2 fermion, its mass is protected by the chiral symmetry, just like in the case of quarks and QED for the mass of the electron. So overall, the energy scale of the Higgs boson is protected in this case. And you can say the Technicolor is actually one such an example of talking about the Higgs as a composite object made of technical quarks, and therefore the understanding energy scale of that becomes natural. So that is the argument of the technical naturalness by Truft. And so that was one of the reasons why we expect such a new particles, hopefully at somewhat higher energy scale. And in the case of supersymmetry, obviously, you expect to see SUSY particles or superpartners to every standard model particle. In the case of compositeness, you expect to see dynamics of compositeness. So you might expect resonances like rho meson, which is basically the parallel spin combination of up and down so that it is a spin one object, as opposed to ion, where the spins are antiparallel. And so this can be viewed as an excited state of pion. And in the case of the proton, of course, you have UUD. And when all the spins of UUD lined up, that is a delta plus spin 3/2 object. That is also a kind of excited state of the proton. And once you actually go to high enough energies, you might actually start to see the constituents directly. So that's the way compositeness theory would work, giving you a multitude of experimental signatures. So that's why we hope
We lost the audio again.
I got disconnected again.
Yeah, there was a brief moment. You were saying you were finding the constituents, and then we lost the audio.
Can you hear me now?
Yeah, now we do.
Okay, good. So I realized that I was accidentally connected to the other Wi-Fi network we had a problem with on the first day. I reconnected to the other one, so hopefully this one is more stable. Okay. Okay, so that's the idea of expecting new particles associated with the electric scale. And certainly we didn't find such associated particles at the LHC energy scale, but it may be just a little bit delayed. And John Ellis actually made this argument that it's better be late than never. And of course, he has been making an argument for supersymmetry at higher energies, like FCCHH, meaning that with 1 TeV SUSY scale, the correction to Higgs mass squared is order 1. If this is 10 TeV, the correction is actually big, or to the 10 to the 4th. But if you actually send this to infinity, which is the non-supersymmetric theory, the correction may be 10 to the 32 times the mass of the Higgs boson, as I talked about before. So it's much better to have 10 to the 4 level of fine-tuning compared to 10 to the 32 level of fine-tuning. That's just a whole different ballpark on the level of how much you have to tune your parameters. And that's what I believe he meant when he said this. Now, in addition to these arguments based on naturalness, which you may or may not buy, there's yet another argument, which I feel a little bit more actually sort of believable, which is that, well, we have never seen a spin zero particle before. And if Higgs boson is spin zero, then that would be really unusual, looking at this list of particles we discovered so far, up, down, electron, neutron, electron, charm, strange, muon, neutrino, muon, top, bottom, tau, neutrino, tau. And we have these force particles, photon, Z, W, and gluon. These are all spin 1/2. These are all spin 1. And the only spin zero particle we know is the Higgs boson, right? And I always felt this was a very artificial theory. And of course, we got all used to it because this is the particle content we see over and over and over again in any talks and in any textbooks and so on and so forth. But if you actually take a step back and look at this once again, what we are doing here is to introduce a particle kind of particle we've never seen before, and let it do the most important job. So when I learned about the standard model back in grad school, I felt like this was a very artificial model. It really looked like a toy model to me. It does what it's supposed to do, but you have to rely on this new kid in town, which never seen before, but it's the most important guy in the whole game. So that was actually something I found very, very unusual. But if you go back to both of these cases, in the case of supersymmetry, Higgs is one of the many spin zero particles. In fact, with including color degrees of freedom and 3 lepton states, so you have 15 particles altogether, and you have 15 complex spin zero particles in a given generation. You have 3 generations of them, so you have 45 of them. And Higgs has only 4 extra degrees of that. 3 spin zero particles. It's one of the many. So there is a context why such a thing exists. So one can even say that supersymmetry predicts scalar particles exist because we know spin 1/2 particles exist, and spin 1/2 particles require spin zero particles to be their partners. So that gives you sort of raison d'etre why such a spin zero particle must exist in nature. So that's one thing supersymmetry does. In the case of compositeness, we already talked about the fact that elementary particles may be spin 1/2. So we are not introducing a brand new type of particle we have never seen before. We are still relying on a particle we are very familiar with, namely spin 1/2, and possibly spin 1 to actually glue them together into the Higgs boson composite object. So there is actually no elementary spin zero particle in this case. So that's another way we can understand the context why such a spin zero particle exists in nature we observed at 125 GeV, because after all, it's not a new type of particle, which is an old type of particle, just like the sigma particle in QCD, which is around 500 MeV or so. And sigma particle, as we know it now, is actually 4-quark bound state, or F naught 500 is actually QQ Q bar state, or tetraquark state, or people call this also the pion, the molecule, which also contains 4 quarks in them. So it is actually some kind of bound state, and that bound state is made of elementary spin 1/2 particles bound together by spin 1 gluons. And so we are not introducing any new particles, but for some reason, this composite dynamics actually force this spin zero particle to condense which is in some sense similar to the fact that signal particle also condenses in QCD, and that's the source of chiral symmetry breaking. So once again, we are looking for this idea that the electrical symmetry breaking must have a fundamental reason behind it. And to understand these reasonings, we also would like to understand the rationale of having this scalar degree of freedom in the theory. And both in the case of supersymmetry and compositeness, they provide answers to both of these questions. Finally, let me finish up now because the time is running up. Yet another idea, which might actually also tell you the context and raison d'etre of spin zero particle, is extra dimension. And if we have extra dimension, just for the sake of argument, we're talking about, say, 4 plus 2, and here's the extra dimension. Spatial dimension, which is a plane, which may be the finite size in a periodic boundary condition. And the Higgs boson may actually be spinning in extra dimension. It may be actually spin one object, but we are living in a direction orthogonal to this 2-dimension where Higgs boson is spinning. And from our 4-dimensional perspective, this extra dimension is so small that we don't actually get to see it, at least so far. So we can perceive the Higgs boson be spinning because we don't have enough resolution to see this motion in this tiny curled up 2 extra dimensions of space. So that's why it looks like it's spin zero. So, but it actually does have secretly spin. And that kind of idea is called Higgs gauge unification. Because if you have a spin one particle in X dimension, that could be the gauge boson, and the remnant of gauge boson used from a 4-dimensional perspective happens to look like the Higgs boson, which is spin zero, apparently, but only apparently. And if you take this kind of point of view, then you would expect that the particles running in this finite curled up dimension has the mass of the order of the inverse size of this extra dimension. And these are what is called the Kaluza-Klein states. And the idea here is something very familiar, which is the problem of the particle in a box in quantum mechanics of the finite size from 0 to r. Then we know the momentum of this particle is quantized in the unit of 2 pi h bar over r. And this is the momentum of the particle, which has to be running in this extra dimension. But if you don't see this extra dimension from a 4-dimensional perspective, this kinetic energy appears to be the rest energy of the particle. And that's nothing but this Kaluza-Klein mass. So namely that if we observe particles that are running in X dimensions, because we can see this running motion of it, we are fooled to think that it is actually the mass of the particle. So we are sort of confusing the kinetic energy with the rest energy because we don't see it's moving. So as a matter of fact, as a result, we expect to see the tower of such particle in masses, and this is what is called the Kaluza-Klein tower. So once again, what we expect to see is a collection or huge collection of new set of particles which may appear at higher energies. So this is yet another motivation why we're talking about going to high energies. And what we talked about yesterday, in order to look back at the electrical symmetry breaking, a few TeV could be already a good enough energy scale to do so. For example, 3 TeV collider would be already fantastic for that job in order to study WW scattering and so on. And of course, higher the better. But if we are building a high energy collider for the purpose of really looking down on the electric scale to gain full understanding, we also secretly can hope to discover new particles at the same time if we have sufficient energy to do so. And that again puts us in the ballpark of 10 TeV kind of power center mass energy scale. So that's yet another motivation where we talk about this. And then I get to talk more about the specific examples like the dark matter example of the weakening interacting massive particles, why they also give us a definite energy scales, why 10 TeV energy scale of the collider can be actually very, very exciting to be built. Okay, I stop here and get some questions.
Thank you, Toshi. Any quick question?
I guess people are tired and hungry.
Quick question, maybe also naive. Suppose you find compositeness or SUSY at 10 TeV at Mon Collider. Would you expect also to understand the fine-tuning mechanism by which the Higgs mass is so small with respect to 10 TeV? TeV?
Yeah, I hope so. So let me actually try to draw one diagram to explain that. So one thing I actually have done in the past is to do a lot of studies on what we may actually learn at the future colliders in the case of both compositeness and supersymmetry. And here's one thing you can expect to do. So the idea why supersymmetry will protect the mass of the Higgs boson, and then we talk about the electron first, is that in supersymmetry, you have a separate superpartner for the left-hand electron and right-hand electron. So there's a notion of chirality even for spin zero particle. And what we have learned from QED example is that the mass of the fermion is protected by chiral symmetry. But by virtue of supersymmetry, this notion of chiral symmetry gets extended to the spin zero particle. And that's why the mass of the spin zero particle, like the Higgs boson, can also be protected. So here, the crucial question, if we ever really discover these supersymmetry particles, to experimentally verify that there is a notion of chirality in spin zero particles. And what you can do in a plus or minus collider, if you can polarize the beam, and this is the superpartner of the one hypercharged gauge boson called Bino, so they can go to a superpartner of their own, and left and right scalar electrons can have different masses, which manifests itself when it decays into electron and Bino. And energy spectrum of the electron, because of this, again, complete understanding of kinematics, has this trapezoid shape where two endpoints are related, are given by the mass of these two particles. And if their masses are different, they will actually show different distributions. So by measuring the energies of the final state from right-handed and left-handed electrons, you can demonstrate that they show different distributions in here, and demonstrate that you can actually have different masses for left and right-handed the electrons, scalar electrons. And by switching the polarization of the beams, you can turn on and off which scalar particles are produced in your final state. So sometimes this disappears and you only see this one. But for the other polarization, you see this one instead, rather than that one. And that way you can demonstrate there's a notion of chirality among spin zero particles based on experimental data. And that would provide you an understanding of how naturalness actually works in practice. So this is just one demonstration that such a thing is possible experimentally. Does that answer your question?
I guess we can resume this at the question time, because I
Okay.
see Andrea is partially convinced.
Okay, partially.
I'm curious if your explanation for the Higgs spin zero was extra dimensions and you had these Kaluza decline towers. I guess this would mean that you would have your next particle at 250 GeV. Is that something where we have enough understanding of if the couplings would be the same? Like, would the couplings be the same as a Higgs boson at 250 GeV? And if so, wouldn't we have already seen it?
That's probably not the way that would work. So the Kaluza-Klein tower depends on what kind of shape the extra dimensions have. And what I drew in picture is as a cartoon that corresponds to flat one dimension. But if you have, for example, the warped extra dimension or whatever shape there may be, then the tower has a different spectra. So Gaussian space, and depending on the shape, you get different spectra. In addition,
I think you're connected
the
again to the
Higgs
wrong
is actually a
Wi-Fi,
question.
Hitoshi.
Oh, okay. Okay, it is in on the correct Wi-Fi, so even that one is a little unstable. So what is going to happen typically is that the Higgs boson would correspond to actually zero mass state, where the closed Klein states are somewhere up there. But Higgs boson, of course, has other interactions in place. So those interactions ended up actually producing a correction to the mass so that it got lifted up from 0 to 125 GeV. And higher states may be multi-TeV. They may also get shifted by a little bit of 125 GeV order, but they basically don't move very much. But for the zero mode, that move is significant. And that is probably the origin of the massive Higgs boson we are seeing in that kind of explanation of the spin zero particle.
Any more questions? Okay. So Hitoshi, we thank you once more. And I think at this point
Okay.
we have to reconvene at 2:15 to get some
2:15.
time for lunch. Yes.
Okay.
Yeah, 2:15.
Okay. All right. I'll see you later.